What if I asked you to tell me how much this ball, how much potential energy this ball has? Could you do so with the information that's on the board? It's just at rest, sitting at the top of the hill. Could you use this to tell me how much energy the ball has? I'm not asking for, I know you guys are diving into your calculators. Come on, guys. Easy numbers here. What's M? What's G? How about we just use 10? That way those pesky calculators don't get in the way. Now, here's the thing. H minus H naught. How much potential energy does it have? The H naught represents what you're going to call the baseline, meaning it's a reference point. So if I ask you for how much potential energy the ball has, what you should always ask back is, with respect to what? I mean, hear me out. Can the ball actually make it here to the very bottom? We don't know what happens past this point, but as long as we're talking about just the yellow slope, the ball can't make it all the way to the bottom line, can it? So if I asked you how much potential energy it has, you could ask, Mr. Shelton, with respect to the very bottom here, or with respect to the bottom of the slope here. And although that sounds like, well, how are we supposed to know what to ask? Part of this is about how functional we want to be. And let me tell you what I mean by that. My stapler could fall off my desk. It could happen. You could bump it. How much potential energy does it have? Well, that's a useful question if I want to know how fast the stapler's going when it hits the ground, right? Knowing how much potential energy. But if I want to know how fast it's going when it hits the ground, I probably only care about how much potential energy it has relative to the ground, because that's where it's going to fall. I don't really need to know how much potential energy it has relative to downstairs. Is there a scenario in which it falls off my desk and lands downstairs? Very unlikely. The H naught is a reminder that we decide where the reference level is. We decide. So gravitational potential energy is not an absolute. It's relative to where the object could go. So if I'm trying to solve for, say, how fast the ball is going when it makes it to the bottom of the slope, I'd probably use this as my reference level. And therefore, everything here, I would say, is 4, right? Going from 2 meters to 6 meters is 4 meters. And therefore, my energy would be 80 joules. But if I'm asked how much energy does it have relative to the ground, well, then I'd probably have to do 2 times 10 times 6, because that'd be the amount of energy relative to the ground. Do we see the difference? Go ahead.
Wait, why is 2 the H? I don't know the name of the symbol there, but why would 2 be that and not the other one?
Why is 2H naught?
Yeah.
It's the lower position.
Okay, got it. Thank you.
You're welcome. The idea is that somebody had to lift the ball to here. Where did it start from? Okay. So remember, all of this is supposed to be in service to helping us solve problems. So, and I want you to watch this for just a minute, okay? What if I ask you, how fast is the ball going when it makes it here? This is kind of like what we were doing yesterday for the lab. All right? Now, if we are dealing with something that's rolling, there's probably no real friction to talk about. So I think the energy I have here will be equal to the energy I have there. We talked about this yesterday, right? The idea that the energy stays the same unless work is done on our system. Our energy here can be comprised of three things: elastic potential, gravitational potential, and kinetic. Those are our three types of energy. It's all we have. Our energy down here, the same. It could be elastic potential, gravitational potential, or kinetic. Everybody good so far? When it's down at the bottom, when it's up at the top, does it have any elastic potential energy? Is it pushed up against a spring or some sort? No. Does it have any gravitational potential energy? Is it above the reference level? Yeah, I think so. Our decision is whether it's 6 meters above the reference level or 2 meters above the, 6 meters above the reference level or 4 meters above the reference level. That's a decision we have to make. So how about we make it right now and say that the red line is our reference level? Is that okay? We're going to do the problem with the red line is our reference level. Everybody got it? So that would mean it would have gravitational potential energy. Now the object's being released from rest. So does it have any kinetic energy? No kinetic energy. All right, so at the bottom, when it makes it to the bottom of the slope, does it have any elastic potential energy? No springs here. Does it have any gravitational potential energy? Now, we said that the red line is our reference level. It's at the reference level. So its height right now is 0 meters above the reference level. So does it have any gravitational potential energy? No. Does it have kinetic energy? Yes, it's rolling. Okay. So mg h minus h naught here has to equal 1/2 mv squared here. Everybody good? Any problem with that? All right. I hope you note right away that the m's cancel out. Do you see that? That's good. All right. So I'm going to have 10 times 4 equals 1/2 v squared. Four times 10, 40. 2 times 40, 80. So v equals the square root of 80. That all good? You guys follow that okay? And yes, you can get the square root of 80 and find out it's 7 point something, whatever. Let's just tuck that away for just a minute. Let's redo the problem. This time, let's set the reference level here. Okay? I'm trying to prove something to you. If I set the reference level there, at the top, do we have elastic potential energy? No. Do we have gravitational potential energy? Yes. Do we have kinetic energy? Is it still being released from rest? So no kinetic energy, that's all we have at the top. At the bottom, do we have elastic potential energy? No. Do we have gravitational potential energy? Yes. So we're above the reference level now. Do we have kinetic energy? Yeah. All right. At the top, we are mg h minus h naught is 6. Is that okay with you guys? That's at the top. At the bottom, we are mg, this time h minus h naught is what? 2 plus 1/2 mv squared. Now, do you notice an m in every single term? Is it in every term? Because sometimes we make this mistake. Do you see an m in every term of this problem? I do see an m in every term in this problem. Do you see a place where there's not an m? There's an m here. That's in this term. There's an m here. That's in this term. And there's an m here. That's in that term. Right? There's an m in every term. So I could factor the m out. But I'm noticing some of you are having trouble with that. So I'm not going to. We're just going to leave it in there. This will be 2 times 10 times 6. This will be 2 times 10 times 2. And this will be 1/2 times 2 times v squared. 2 times 10 times 6 is 120. 2 times 10 times 2 is 40. 1/2 times 2 is 1. Trying to get v, right? So 120 minus 40 is what? 80. 80 equals v squared. Right? Do you see what I mean by saying the reference level is arbitrary? Do you notice you get the same answer regardless? You can choose any place you want to be your reference level when you do a problem like this. You just have to be consistent. Did everybody see that okay? All right. Let's make sure we handle this clearly. Network. There's 3 ways to deal with it. First way, calculate the work. From each force and add them together. That was the first way. We did that a couple times. This next way, we didn't do. We could, we just didn't. We can find the net force. Or use MA, right? Net force equals MA. Correct? Second law. I'll even put that in parentheses. So in parentheses, I'm going to put what this would look like. We didn't do an example of that. But I did use an example of that for the third thing. The third thing the network is the change in kinetic energy. So if you know the change in velocity of an object, you can calculate the network without calculating any other kind of forces and stuff. Just 1/2 mv squared minus 1/2 mv naught squared. 3 ways to calculate network. But that's all for me to say one thing to you. Okay, so we got this written down. I'm pausing for effect, but all right, ready? If network equals 0, then the energy before equals the energy after. I wrote it like this: delta U plus delta U plus delta K equals 0. That allows us to say the energy before equals the energy after. If you'll remember, it looked like this. UE final plus UG final plus K final equals UE initial plus UG initial plus K initial. Right? The energy before equals the energy after. That's what we based our lab on yesterday. Now here's something that's more valuable, or at least more complicated. If the network doesn't equal 0, then this doesn't equal 0, it equals the net work. Which means this would have the net work here. If the network is positive, then the object has more energy afterwards than before. If the network is negative, then the object has less energy than it had before. So if friction does network, you've probably got less energy afterwards than you had before. But like on Cheetah Hunt, if you happen to go over the part of the track where that magnetic field acts on the cars and shoots it forwards, then you probably added energy to the system, right? Because you're suddenly going faster than you were before. Okay? This is just a review of all the stuff we talked about last week. So, I want to talk about situations for the time being where net work equals 0. I have a situation I want you to consider. It's like one of your homework questions. All right. So imagine I have a ramp that looks like this, okay? And over on this side, I have a spring. And it has an unknown spring constant. We'll ignore that pesky friction for right now. Two-kilogram box right there next to the spring. I pull the box back 25 centimeters, about this far, and I let it go. Okay? The box shoots up and makes it to a point that is 1.25 meters above the ramp. I'd like to know what the spring constant was. Okay? So again, I pull the box back and release it. It goes along this road, up into the air, and gets 1.5 meters above the ramp, stops, and comes back down. I'd like to know what the spring constant is. So first, this is a conservation of energy question. And there's a lot of reasons why and things that you can look at that would help you determine that conservation of energy is the best way to do this problem. You could not use forces to do this problem. The force from the spring changes all the time. So you can't use the force from the spring to tell you how fast the box is going. There's another clue, and I'm going to give you several clues as how you know a problem is likely solvable by conservation of energy. So thing number one is a spring is involved. If spring is involved, you're likely looking at a conservation of energy question. Thing number two, and this one's more important, we are trying to figure out the height that something attains. That's a dead giveaway that we're likely looking at a conservation of energy question. The third thing, it involves the comparison of two different states, an initial state and a final state. Those are three big like clues that you're going to use conservation of energy. Again, thing number one, a spring is involved. Thing number two, you're measuring something's height. Thing number three, you're going to be comparing two states. Now there's a fourth thing to add to this list, and that is if you're asked to figure out how fast something is going. Those four things generally are conservation of energy questions. And look, we couldn't use anything else to do this. The ramp is curved, so we couldn't use stuff like forces for inclined planes there. It's not a projectile problem because we don't see how far away it lands on the ground somewhere. It's asking about the spring, but it tells us how high it goes. That's a good idea. It's a conservation of energy question. What you have to do afterwards is pretty straightforward. I'm going to explain it like there's a set of steps, but I probably won't use steps very often for this. The first thing you should identify is, are there two clear states of the problem? Is there an initial state and a final state? In this case, I think there are. There's the initial state where the box has been pulled back against the spring. And there's the final state where the box makes it to some height. You guys see that as two possible states? When observing each state, you should ask yourself, what kind of energy does the object have at each state? It can have more than one kind at a time. So that means going through and considering what possible energies are at each state. Before you identify the energies, it makes sense to establish a baseline, a reference level. And now, the reference level is arbitrary. You can put it anywhere you want, but does it make sense to you that this should be my reference level? The lowest point in your problem is usually the best reference level. The lowest point the object can attain is usually the best reference level. All right, so based on that, when I pull the object back up against the spring, right when I release it, does it have any kinetic energy at that instant if it's being released from rest? No. Does it have any gravitational potential energy when it's pulled back against the spring? Is it above the reference level? No. Is it backed up against the spring? Then it's got elastic potential energy. All right, that's our initial state. Our final state. Is the object moving when it reaches its highest point? No, highest point. Remember, that's when the object stops. If it was moving, it's either still going up or still going down or moving sideways. But in this case, it could only be moving upwards, right? So we know it stopped. So that means no kinetic energy. Is it above the reference level? So it most certainly has gravitational potential energy. Is it pressed up against a spring or a piece of elastic? No, so no elastic potential energy. That leaves us with mgh minus h naught. The reason I write h minus h naught is to remind you, did you decide on a reference level? If you did, you've handled the idea of what h naught means. Do you know how high above the reference level your object is? How high? 1.25 meters. I'm not trying to trick you. As long as you know how high above the reference level, you're good. So we're going to set this state, our final state, equal to our initial state. So 1/2 k delta x squared equals mg h minus h naught. you do notice in this one, H is not going to cancel out, right? I'm sorry, M is not going to cancel out. I do not have an M in every term. So that happens. So we'll do 1/2 K. Delta X is 25 centimeters, but I also gave this value in meters. What should we do here? Change it to meters. Yep, put it in meters. G is always going to be in meters, so this is the right way to go. That is equal mg times h minus h naught 1.25. Do you think you could successfully figure out what K is with the information presented? Okay, take a second. I'll take a break. An actual test gets you what, like 1 point? So this is not that big a deal, but you should be able to do your arithmetic. Especially if the next part of the question asks you stuff. Go ahead. Well, when I multiply this side all together, 2 times 10 times 1.25, I get 25. And then this side, it's 0.5 times, it's 0.5 times 0.25 squared. And that gave me 0.03125 times K. So when I do 25 divided by 0.03125, I get 800. Does that make sense? Yeah. Okay. All right. What was the fastest the box went? Do you know what I'm asking you to figure out? Now, in asking this question, I'm not telling you where it was traveling the fastest, but does it really matter? Do you understand that once it left the spring, it's probably traveling the same speed all along here? Does that make sense? And are you pretty clear that it would start slowing down once it went up the ramp? So it doesn't really matter where you place the box down on this ramp. It's probably got the same speed anywhere because there's no friction. There's a couple different ways you could figure out this answer. Now that you know the spring constant, you have more than one way to do this one. Choose the way you think you should do it. I know how I would do it. I want to see what you would do. So think on it and see what you would do, and then I'll tell you how I would have done it. What kind of energy does the box have here? Does it have any other? Is it pressed up against the spring? Is it above the reference level? So just kinetic, right? We already found out that it had 25 joules of energy here. You could just set this equal to 25 joules and then find your speed. Folks,